Hey guys, welcome back. In the last video, we talked about what nuclear decay was. Now we're going to dive into stability, predicting. And when we talk about predicting, I just want you guys in this course to be able that it would predict and what would be a possible option. Okay, because not all nuclei are stable. One of the ways we can predict if a nuclear is stable is if you look at this chart, it's figure 25 in your figure 20.5 in your book. Gives you the zone of stability, right? This is stable nuclides in the zone of stability. As you can see, we start off hydrogen, helium, lithium, right? We start to get a 1-to-1 ratio of protons to neutrons. But what happens is, because of how atoms work and what holds them together, that ratio goes from 1 proton to 1 neutron to 1 proton and 1.5 neutrons, right? And so we can be either too many neutrons or we can have too few neutrons. And so if we have too many neutrons, a lot of times we will have beta decay. Right? If we have too many protons, too little neutrons, a lot of times we get either positron emission or electron capture. Right? And so if you look at the examples here, both of them were changing with an electron. We're either losing the electron or we are losing a positive electron. Okay. Now there are some magic numbers, as you can see, and those are particularly stable isotopes. Helium and oxygen and calcium. Right? See, these are nice. All right. Anyway, that's what we want to do. So if we look, the example here, I got carbon 14. Well, carbon 14 is not stable. It has too many neutrons. So what happens, beta decays, turns into nitrogen. Same mass, but one less proton. Or one more proton, one more proton. Potassium 38, all right? Emits a positron, becomes argon. And just give us better ratios. So that's all we're talking about with this. That's all I really want to talk about. Let's talk about what happens. And this, when I was in your shoes, kind of surprised me, right? Because I didn't think about it. It caught me off guard. So fluorine 19. Fluorine is one of those mononucleic isotopes. There's only one naturally occurring isotope of fluorine, fluorine 19. But it has a mass of 18.9984 AMU. All right. And so if you do 9 protons times the 1.007825 AMU, you get 9.0745, as you can see on the screen, AMU. The 10 neutrons gives times the mass of a neutron. Right? However, that gives us a different mass, doesn't it? That gives us a mass of 19.15708 AMU. However, on the periodic table, it says it's 18.998403, and it can keep going, right? So that's not, the periodic table is different than what we should calculate, which is weird. And so the difference there between 19.15708 minus the 18.9984 is 0.1587 AMU. All right. So what happens is this mass gets converted into energy for the binding of this nucleus. It's kind of neat. And so finally, we get to use the famous E equals mc squared equation in this chemistry. Finally. Okay, so what do we have here? All right. So now, when we're using energy, right? Energy is in joules. All right. If you remember, a joule is a J, which is a what? All right. Newton meter. So joules are newton meters. So if you break it down, joules equals a newton meter, right? What's a newton? Newton is force, mass times acceleration, right? So kilogram meter squared per second squared is a joule. So that's kilogram meter squared second squared. The important thing I'm pointing out here is this guy. So whenever we're dealing with energy, our masses have to be in kilograms. All right. So in chemistry, we're always in grams, sometimes milligrams. Right now, whenever we're doing energy, we had to do this way back in the light chapter in Chem 1. We still had to go, when we were doing with energy, we had to go to kilograms again. Okay. So right now, my energy is equal to M 0.1587 AMU, right? And then the speed of light, 3.00 times 10 to the 8 meters per second squared. Well, I don't like the AMU. Again, we just talked about this. We have to go to kilograms. So how do I do that? I'm going to do that on the side here. 0.1587 AMU. Right? I don't know why I did that. Times. Right? Well, AMUs have to go on the bottom. So if you look, it's 6.022 times 10 to the 26th AMU is 1 kilogram. Right? So all I have to do here is divide by 6.022 times 10 to the 26 kilograms, and I'll get my answer. And this looks like it should be 2.37 times 10 to negative 11 joules per nucleus. Well, that's funny. So that's how many, it doesn't sound like a huge amount of energy, but again, think how small this thing is. Now, if we want to talk about this per mole, right? If we want to do it per mole, we can do it per mole as well. So if I go to E equals mc squared, same thing. E, instead of using 0.1587 AMU, I'm going to use 0.1587 grams. All right. And we know, I'm just going to convert that into mass. 1,000 grams is a kilogram. Right? So there's my mass. C, 3 times 10 to the 8 meters per second squared. Right? Okay. Because a joule, and if I do the units, right, that becomes kilogram, meter squared, second squared. It's a joule. That'll give me about 1.4 times 10 to the 13th joules per mole. Or 1.4 times 10 to the 10th kilojoules per mole. That's a lot of energy. It is a lot of energy. All right. And so, because of that, we try to utilize that energy. And we'd like to. We'd like to utilize that energy. And so how much energy do we have? Well, if we look, it's a maximum in iron. But these are the nuclear binding energies per nuclei. Right? What's holding them together. All right. Let's talk the K series real quick. And so we talked about there are 3 naturally occurring radioactive decay series. We got uranium and thorium. And so here's an example. Do you have to memorize this? Please do not memorize this. Uranium goes to thorium. Now this is a big deal. This is a huge deal because chemists before this time did not think this could happen, right? Because this is nuclear chemistry. You're taking the building blocks and you're actually changing the building blocks. The building blocks themselves are changing, not the actual, like, you're taking, I don't know, nitrogen and hydrogen and making ammonia, or hydrogen and oxygen and making water. This, you're actually taking uranium and making a new element, thorium. Big deal, right? And you look at the half-lives, right? There's all over the place. 4.5 billion years to 24 days, right? So, hours. Then we got 6 hours. But this is the decay series to get to lead, which is stable. So lead's stable, uranium's not. This, all right? So the next video, we're going to talk about how we're going to harness this energy if possible.